can start.
Yeah. Okay. So thank you very much, Prof. Dominic, for the very kind introduction. So I'll try I'll try to keep up with all of those nice words. Yeah. Let me share something. A minute. Yeah. A minute. Yeah. I don't know why is this very slow. Okay.
Coming up.
Eh.
Oh, by the way, Zufan is from GTS Group Technical Solution, right?
Yeah.
That's his signage. Hey, what is PDNT? Process Design and Technology.
What is this? PDNT is Project Delivery and Technology. Okay. Yeah. Hello. Sorry. Yeah. Sorry.
Oh, you came back in.
I clicked something.
Press the wrong button.
Yeah, I clicked something. I have to redo this. Why is it now? Sorry. It's okay. Oh, I'm sharing the slide. Let's share the slide.
Okay. You're back here again. Okay. Good.
Okay. Yeah. I think you can see my slide. Yeah.
Can. Yep.
Okay. Okay. So again, thank you very much, Prof. Dominic, for the kind introduction and then for the opportunity given to me to at least to share something that at least for me it's very much interesting. And then I think I can share this interest with these young engineers and our future engineers as well. Yeah. I understand from Prof. Dominic that all of you are in the year 3 and then just started doing simulation for your how do you call it? Am I sharing my camera? Okay. For your post design, yeah. So what I'm about to share here is I think a little bit more on continuation, because last year we have one of our colleagues, Shahrul Azman, also shared something about simulation in also in the class of Dominic. So he talked about a little bit on the future of the simulation, and then I think the future is, we can say that the future is now. So I'm sharing with you. Hopefully, I can get it done in half an hour or 40 minutes or so that we can have more ample time for Q&A. If you have any questions, just feel free to ask, or type in the chat box. So later on we can just go through it and let's see if I can answer you all of your questions. But feel free to ask. So I'm going to share with you is the current buzzwords, that we have been seeing so far in this digital era of yours. Basically, we see the buzzwords like artificial intelligence. We see buzzwords like machine learning, industrial revolution 4.0. We see data analytics and so on and so forth. So and then I'm in this session I'm going to share a little bit on the AI, or artificial intelligence, in chemical engineering, and then more specifically on the hybrid modeling and process simulations, because you guys are, or ladies, guys busy with process simulation. I'm going to share a little bit more deeper on hybrid modeling and process simulation. So it's not just first principle process modeling as we know up until now. So I'll divide my talk into I will introduce to you what is AI. I mean, at least from my perspective, what I know, and then we'll see if there is any connection between AI and chemical engineering, because most people see that it is AI is more like a computer science. It's more like IT and stuff. So what does it have anything to do with chemical engineering. And then lastly, I will then show about the hybrid modeling and process simulation, and then how we internally petronas how we use this hybrid modeling. So what is AI? So if you guys, I think you know about this Terminator stuff, yeah. So this AI, if you hear a word like AI, and then what we have in mind because of these Hollywood movies and stuff, what we have in mind is this the Skynet. So the Skynet is the neural net based artificial intelligence. It says here, I don't know if it's true, but nonetheless, so these robots think that humans are the cause for the planet destruction. So we have the CO2 global warming, we have forest fire, we have everything. We are destroying the planet Earth. So this computer, because it's very intelligent, it says that the human is then the major cause of planet's destruction. So we'll have to then destroy the humans first in order to save the planet. So that's been basically the idea of this Terminator. Yeah. So that's then the AI from the Hollywood, and then there's another Hollywood movie. So the same concept of AI. Think you know this Avengers, yeah? This is Tony Stark with the Iron Man. So he uses the AI to help at least to do some justice, and then to help people from the aliens attack, so to say. So one AI in the Terminator, these robots are killing humans, and then the other AI in this Jarvis, and then the one so whatnot. So he uses AI to help him also helping humanity, so to say. So that's about the Hollywood movies about the AI, and then what happens in the real life. So in real life, I think in 1997, Gary Kasparov has been beaten by the first neural network artificial intelligence computer in the chess player. Yeah. So and then about 20 years after that, in 2017, this Alphago has beaten the human's best Go player in 2017, because this compared to chess, this Go it's very complicated. It's much more complex with limitless combinations, and then and now people or the programmers, they are now developing OpenAI to use what they call like reinforcement learning algorithm, so that they can then beat humans StarCraft's best player. So I think all of you who knows how to play, all of you who knows video games, so not StarCraft is then not so strange to you. So apart from the movies, and then from the games and sports, and we have been seeing these applications of AI in our daily life. For example, in marketing, in travel. Yeah, in travel we can see this Google Map, for example, the easiest one. So it can then tell us what is then the fastest, and then or the quickest or the shortest routes, and then it also can predict the from the eyes. So this Google, they have the algorithm from the image of the eyes. They can then predict whether one patient has this diabetes or whatnot. And then it's also like a self-driving car, and so on and so forth. There's also in social media, the one that we are very, very consumed a lot by the social media. So if we search something in Facebook or Meta now, if we search something in Google as well, so the next day or the next click, it will be then recommended a web page, or recommended videos, or recommended articles run by these algorithms behind the scene. Yeah. So it can then I think they can then bombard us with all of these similar that might interest us, so that it will then take our attention, basically. Basically, what are they? I mean, I took this definition from this article. I think you need to see this professor called Venkat Subramaniam. So he wrote this article in AICHE journal. So he says that this artificial intelligence is then the study of how to make computers do things at which, at the moment, people are better. So it's more like things that are repetitive, things that need more power, things that need more speed, and so on and so forth. So those aspects of life, they are now being or are going to be taken care of by robots or by computers. We can see in this AI there are several subfields like visions or speech. Yeah, vision. So I think if you know the lead scientist for Microsoft for the visions is a blind person. Yeah, it's a blind engineer. I don't remember his name, but he's a blind engineer. So he's then busy with his team developing visions AI for Microsoft. And so also for the speech, I think I saw one like short videos on how people then able to reconstruct our own voice. And then also language processing, expert system, robotics, and then what we now in our process industries, we are now busy with the machine learning part of artificial intelligence. And then from this machine learning, we can then do some predictive, what we call predictive analytics, or in our old chemical engineering term, we call it process optimization. But nowadays, they call it predictive analytics. This machine learning, there are three types of machine learning. So I'm just lay things out for you so that you can have an idea. Yeah, I'm not really sure if any of these things that I'm going to talk to you will make sense, but hopefully it will then make sense in maybe after you graduate or whatnot. So when you work in this field, then you know. So this machine learning, it has three like branches. So it has like supervised learning. We call this in our chemical engineering education as regression. So regression. So we have the X variables or the independent variables, and we have the Y variables or the dependent variables. So for example, Y equals to mx plus c. So if we have a bunch of data of X and then a bunch of data of Y, then we can then make, or we can calculate the M and then you can calculate the C, so that we know what is M and C in such a way that the model that Y equals to mx plus C fits the data better. So that's the supervised learning. Yeah? We see this in thermodynamic models. We see this in Q equals to MCP delta T. We see this in all of these like constants that we know, the pi and so on and so forth. So all of these are parameters that we get in such a way that we can then fit the data. And then another one is then unsupervised learning. So this unsupervised learning is more in statistical terms. So we can then from our for example, in our mass balance, we have our pressure, temperature, flow rates, and then timing as well. So this supervised learning is then to dig what is then behind the data. Is there any pattern? So the temperature today, does it have any differences with the temperature yesterday, or the flow rate of yesterday, or the pressure a few months ago? So if the current operating is then the same compared to the 1 year before. So all of this unsupervised learning is then to trying to get or trying to aggregate data together so that we can see if there is any pattern, so that we can see if there is any correlations that we can derive, any insights that we can get. Yeah. And then lastly is then the more advanced part of machine learning, the reinforcement learning. So it's more like how we study. So for example, at school, if we score, we will get like a prize. Yeah, we'll get a prize. So and then we will then psychologically we will then work harder or work smarter so that we can then score more. If we don't score, we will then slacking off or we get lazy, so we will get some punishment. So this reward and punishment is then part of the algorithms within the reinforcement learning. So it allows computers to learn by itself by this carrot and stick or rewards and punishment in such a way that it can then by millions of runs of simulations. Like this Alphago, like in this Alphago and then StarCraft. So they run these simulations millions of times, so that this computer, it can beat, or it can have these millions of years of experience, so to say. Yeah? And then the last part of it, which I would like to explain, is that like a descriptive analytics. So, for example, you guys are now simulating a plant, right? So you develop the process, and then from this process, we make the simulation model, and then we can then create the mass and energy balance. So it's more like a descriptive. So we describe how much is then the flow rate, how much is then the temperature, how much is then the pressure, and so on and so forth. So it's more like what we do currently, where we then calculate mass and energy balance. So in the plants as well, we get the data, and then we try to make sense of that by again calculating the mass and energy balance based on the data that we have. Once we get the model to calculate that mass and energy balance, we go to the predictive. What are the trends? The predictive analytics. So this is more like once we get our model, if we do like a case study. So if we increase the flow rate, for example, if we increase the outlet pressure, what happens to the power? So if we increase the flow rate, what happens to the duty? So things like that we can then see and then we can make a prediction. So if I increase this by 10%, will I make like will I increase the duty by also 10%, for example? So it's more like this predictive. And then the last one is then the prescriptive analytics. So it's more like what I said, optimization. Yeah. So I think I was mistaken here. So prescriptive analytics is then the optimization part. So it's more like so now we want to go, for example, from Nottingham campus to KLCC, for example, and then we can then ask Google to say, okay, now I want to go from Nottingham campus to KLCC. Which route should I take? Should I then it will then give us 3 or 4 options. One is then the shortest, and then the quickest, and then maybe it's somewhere in between or whatnot. So it's more like giving us what should be the flow rate, the temperature, or the pressure in such a way that we can then maybe increase the value, increase the profit, increase the yields or whatnot. Yeah, so it's more like an optimization, so to say, in our chemical engineering language. So having explained this and then trying to connect these terms as much as possible to chemical engineering field, let's hear the expert. So I think you need to go to this Google. You can search in YouTube. Venkat Subramaniam on artificial intelligence in chemical engineering. It's 10 minutes, so I think we don't have time for that, but I'll just show it here so that you can YouTube this yourself. Yeah. So this professor, he wrote this article. So it's open access article, so we can read it. So he lays down this historical AI in chemical engineering. So it says that around 1960s, yeah, so it's much older than all of us combined. So 1960s, 1970s, there was then the first what they call AI effort in chemical engineering with this adaptive initial design synthesizer system by Sirola and Root for process synthesis. And there are many other stuffs, but I just take the major points that I think I understand. And then 10 years later, 1980s, 1990s, the design expert era. So it's more like a decision tree, if I can understand it very well. So if we want to design a reactor, shall we go for the CSTR, or shall we go for the PFR, or shall we go for the batch? So all of this, it has some merits. Yeah, it has these advantages and disadvantages. And then once we have our own consideration, we can then go further along this decision tree. So that all in all, these decision trees are becoming the expert system that we can follow in such a way that we can then, in the end, we end up with the best design, yeah, so to say. But again, this expert system requires lots of effort, time, and money to develop because it needs human brain and then put it into such of decision trees. And then 1990s until 2000, that's then the era of neural network. The era of neural network, where this method or algorithms is then used in process modeling, in control and fault diagnosis, and so on and so forth. Comparing this AI, so this neural network expert system and stuff, comparing this in this period with model predictive control, yeah, MPC, or process optimization, which is more straightforward. This AI is a bit lacking. It's a bit lacking because, yeah, it needs lots of efforts. It needs huge computational technology, and then at the time it was not there. But then now, in 2005 and until now, we have all of these supercomputers. We have access to internet. We have access to lots of data, and then there are many open source software like this Python. They are free, yeah, for anybody to use. So we can learn ourselves, and then we can then use it to the best of our advantage. And then I quote him here. So what we did in the end, with all of these simulations and modeling and stuff, in the end, what we desire are first principles-based understanding and insights of the underlying phenomena that can be modeled to aid us in rational decision making. So in the end, once we get our model from the data that we have or from the information that we have, we would like to use this model, either it is first principle based or data analytics based, in such a way that it can then help us in making a better and faster decision making. So there are some articles as well. I think it's good for you if then to read this. Yeah. So it's from Venki Yu, and then it's also from Data Science and Chemical Engineering. I think chemical engineering curriculum. I think nowadays there are many already universities trying to incorporate data science or data analytics. We call this data analytics statistical analysis in the past, but nowadays it's more fancy to say it like data science. So hybrid modeling. So where is this hybrid modeling located? Yeah. Before I hybrid modeling in process simulation. So I'm sure that you know what process simulation is, but I have a video from cars, which I think it's worthwhile to watch here. It's
Zufan, does it contain sound?
it's can you hear the sound?
Here we go.
I think so, yeah.
How do I do this? Come on, baby.
Mr. McQueen.
Cruz, thank you for the old man training, as crazy as it was, but I'm warmed up enough, and now I need you to launch this thing.
Mr. McQueen, wait until you can handle it, please. There are no shortcuts.
Okay, we'll just see about that.
All right, my star racer is on the simulator.
Why, yes, I am.
Well, let's see you take it out for a spin.
Right away, Mr. Sterling. Owner of the company.
Okay, have fun.
This is what I'm talking about. Whoa, didn't know about those.
Prepare to race.
What did it say? Is it
The
talking?
green flag is
I
out.
don't see the flag. What do I do?
Go.
Go?
Go.
Oh, that's sensitive.
You have hit a wall.
Shouldn't be this hard, should it?
You have hit a wall.
You're fighting a simulator. Just race like you always do.
You have hit a wall.
There can't be this many walls on a regular track.
You have been passed by Jackson Storm.
Wait, Storm's in here?
For motivation. Storm races at 2:07. Pick it up, Mr. McQueen.
I'm trying.
You have hit a wall.
Mr. McQueen, come down from there and we'll work you up to this.
I am fine, Cruz. I can do it, okay? Whoa, 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 whoa!
You have jumped a barrier.
Sorry.
You have maimed 2 vehicles. You have destroyed a drinking fountain. You have disabled an ambulance. You are on fire. Danger. Danger. You are going the wrong way.
Look out, look out! Turn it off, turn it off! Get these things off of me!
You have crashed. You have crashed.
Are you all right?
You have crashed.
I've crashed.
So I think we can have an idea of what process simulation really is. Yeah. So it's more like we have in this case we have an artificial environment where we can then do whatever we want, and then in reality we are not on the field like that, but then we can then sense, or we can then see what happens if we change. If we increase the speed, or if we increase the pressure, if we increase the flow rate, or if we reduce the flow, the temperature, and so on and so forth. So that is then the process simulation. There are many process simulation software available for us to use. Yeah. Many of them are like commercial software. Like in our case, in Petronas, we are using the product of Symmetry, Schlumberger, which is then very much similar to Aspen HiSys. Very much similar to Aspen HiSys. So if you know how to use HiSys, because HiSys is then one of the first to enter the market, so they are more well known. So if you know how to use HiSys, you know then very much how to use Symmetry. We have also from Aspen Tech, they also have instead of HiSys, they also have like Aspen Plus, and then they have this Aspen Exchanger Design and Rating as another toolbox. We have also like a Pro 2 from Aviva. We have PetroSim, which is also very similar to Aspen HiSys. We have GPROMs from PSE, and then they are now under Siemens. We have also like a Mobatech modeler. I don't know if you're aware of it, but one of my friends, he founded this company, and then they make it in the Mobatech company. And we also have like a Unisim, which is very much similar as well with PetroSim and then HiSys. This Unisim is under Honeywell. And then I put here as well two. It may not be like you may not be familiar with them, but they are there. So DWSim, and then COCO. So COCO means Cape Open for Cape Open Process Simulation, something like that. So these two are open source software, so you can just freely, you can just download it for free and then use it, for your own risk. Yeah. So they have like a basic thermodynamic models there, and then conventional unit operations are also there. And then the DWSIM, they also have this hybrid modeling feature in it. If you would like to try, just Google these two, and then you can get them for free. While the rest, you need to have license from your university, if they have it. Why do we do process simulations? If any one of you knows why we do process simulation, maybe you can just type it on the chat functions. But nonetheless, I will just share what I've done with process simulation. Typically, what we do with this process simulation, like what we are now doing in your process design class, we calculate mass and energy balance, and then from this mass and energy balance, we then use the information to design the equipment, design the unit operations or the process equipment, basically. So that's one of the fundamental or the easiest way why we do process simulation. And then number two is then help finding root cause of problems, because we can see from the plants, we can have readings, and then from these readings we can then try to calculate what actually is, or what should be the flow rate, what should be the temperature and pressure, in such a way that it will then obey our first principle. It obeys the mass and energy balance. So if the mass is not balanced, for example, and there must be something wrong, there must be some leaking, there must be some additional heat or loss of heat somewhere. So that's more on this finding of the root cause of problems in our plants. And then number three is more like once we have the model correctly modeled, the plant correctly modeled, and then we can then do more sensitivity analysis. We can do like a process optimization. We can see to increase the yield or to increase the profit of this plant. What should we do for that stream, for that compressor, or for that distillation column? What should we do there? So it's more on this item. And then number four is then to evaluate the dynamic situation for process safety and control. And then this number five is more like if we have like a new process, if we have like a new raw materials, or if we have a new catalytic system, we can then make a model and then see what happens with the technically what happens, and then economically, and also like a safety and then profitability and so on and so forth, like this 3P for sustainability. Along with that, it can also show the research direction. For example, if we have like a new catalytic system, it has a certain kinetics, it has a certain base at a certain temperature, it has then a certain value of conversions and selectivity, and then because of this selectivity, for example, it can then create many unwanted products. So these unwanted products, they need to be separated. So then our job is then now using the current technology of separation, can it do the work in a cheaper way or in an easier way? If not, then we need to research more on a specific separation system in such a way that in the end the plant will be profitable. So that's one example of this showing research directions in R&D. The last one is then to evaluate modifications. So if you want to increase the capacity, if you want to change the or because of tighter regulations, we want to reduce the waste. So things like that, we can then use this process simulation so that we know what we should do. Lastly, I would say, so this is it for me. Just make the mass balance of your plants or your process, and then you will see problems. And then there should always be like rooms for improvements. Now that's then about the simulations. Now, why is hybrid, and why is hybrid, by the way? So this hybrid is then refers to the situations where we have on one hand we have a first principle. This first principle, what I mean by first principle modeling is that the ones that we have been using so far, so this mass energy balance, this thermodynamic model, all of this is more on a mechanistic way that we understand. So if we open a valve, the flow rate will increase depending on the size of the pipe, and then depending on the density and then viscosity of the fluid. So we know this. So that's our physics-based understanding or first principle-based understanding. On the other part, we have a process very complicated. For example, membrane. For example, it is not found in all conventional process simulation software, but we have like experimental data for the retentate or permeate of this particular membrane, and different membranes, it has a different properties, it has a different characteristics. So we have the data, but we don't have quite the physics based model for that membrane. So using the data, we can then make a regression, for example, simple regressions of linear regressions like y equals to mx plus c. So we can then model that, and then put that model, that y equals to mx plus c, into our process simulation software in such a way that the inlet of the membrane is then calculated by the HYSYS, for example, or vice or symmetry, and then it is then being calculated into these regressions, and then outlet of the regression, the output of that regression is then being sent again to the process simulation environment. So this hybrid is more like combining first principle based and then data driven model. Why we do so? Because number one, we don't have that physics-based model, or we don't understand it well enough in terms of the mechanistic detail. Another one is that what I see is that we have like a new and complex chemicals which we don't know what the properties really are, because all of these thermodynamics, they are historically developed based on like oil and gas or hydrocarbon-based chemicals. But chemicals like polymers or solids, heavies, all of these very complicated, they are not very well known. They're not very well known, and hence because they are not known, if we can measure their properties, for example density, and then with the variation concentrations, so that we can use this varying concentrations as the x, and then the density as the y, and then we can then make a correlation between the y and x. So it's also a reason why we can do, or we have to do, to this hybrid modeling. How is it then progressing? As we understood from the paper of that Professor Venkat Subramanian, so in the early 1980s, 1990s, that is then the era of a neural network. So this hybrid modeling has already been started around those years, 1992, 1994. You can read the articles over here. And then while the industries, as we know it, so AspenTech just embrace it only now. Yeah. So we have about 30 years from research to the industrial application. So it took 30 years to appear in industries. So AspenTech in 2021, with the latest release, I think they are now with version 12.2, but starting from version 12.1, they have already these 3 parts of AI, what they call industrial AI. So they have this AI-driven hybrid modeling, the reduced order model. The AI-driven hybrid modeling is the one that we have been talking about. So we have the process simulations, and then we have also like data-driven models where we combine them together. Reduced order model is then we have a simulations, for example, distillation column, and because distillation column is very difficult to converge, so we just then need to run a couple of experimental run on these simulations, these distillation columns, and then use that data to make a regression. So that regression is what we call as reduced order model. The last one is that what they call, like, for example, we don't have any fouling factor. We don't know what the fouling factor. We don't know what the overall heat transfer coefficient is, but we do know the flow rate inlet, the temperature inlet, and then temperature outlet, from which we can then make a correlation, how much is then the overall heat transfer coefficient, for example, and that is then taken care of by these third options in AspenTech software. And Schlumberger, this is the one that we are using internally in Petronas. This latest version of 2021.2, it releases this AI or neural network based hybrid modeling. So this one is a black box of neural network model where it takes the input from the process simulation software, it calculates the output, and then it then sends back to the process simulation software basically. So I think you can relate this to your HYSYS interface. Yeah, so it's very similar. So the concept is more like so we have the data, and then we can either we have the machine learning models, we have the process simulation model. Sometimes we, based on the data that we have, we can make the unit operations and then apply that unit operation into the process simulation model. That's one way. Or from this process simulation model, we can also calculate the properties, for example, the density, concentrations, refractive index, and so on and so forth, so that we can use that data as a part of the machine learning model, so that we can then create another model where we can then deploy as a web page or whatnot. And then from these two models, we can make our decision and action. So it's more like a very very on the surface definition that I giving you. So the workflow that we have been doing. So we have again, I'm just repeating myself, but just to for the benefit of repeating, we have the process simulation software, we have the plant data. So we combine these two sources of information. From there, we can then develop all kinds of machine learning models, like this neural network or decision tree based, or just simple regressions like linear regressions, like multilinear regressions, or also non-linear regressions. Yeah. And then from this model, we can use this model. For optimization or for multi-objective optimization for decision making in the end. So I put here like this Google Map figure, so that we can have an idea how this model is being used. So in this case, I would say that this is like a Google Map of process plants or prescriptive analytics, what we say. So we have the model of the plant, and then we have, like in this case, in this example, we have sustainability assessment, the technical assessments, and then the life cycle assessments, and then the safety assessments. So these three objective functions, they are typically they have a counter effect. So if we want to increase the profit, that means we may sacrifice on the safety, or we may sacrifice on the environment. But if we take all of these three into account altogether, we end up with multi-objective optimizations, and then we can then solve this with Pareto front generator, and then later on we can do the multi-criteria decision-making approach. Examples that we have done so far internally. So we have deployed this. So we have this like a landing page, for our gas dehydration unit, and then cone destabilization. So this is then my example, destabilization unit. So it's a unit. It has a series of heat exchangers, flash vessels, and then columns. That stabilizer column. And then the goal is then to get the RVP below 12. So this RVP below 12. So we can then these are like, for example, these are like real tech names that we can then control. So if we then change these numbers, we can then have a predictions of what would be the RVP, the rate vapor pressure, and what would be the RVP of the gasoline, for example. And then we can know. So if we want to make it like 8.22, so that means I have to run this like 59, this then 48, 114, and all of these informations we give it to the operator on the side, so that they can then use it as their set points, so to say. Another one is that we use it as a benchmark. So this one is that what we call the ideal target. So to get this water dew point and then the reboiler. So to get to the same water dew point, what is then the minimum reboiler duty? So this is then our like a theoretical target. This is then the data that we are collecting in the plants. So we know with the handles or the operational variables that they have been doing, they are far away from the ideal target. So it shows like where they can go, theoretically. So the aim is then to change independent variables or the X around this area in such a way that they can then reduce the energy consumption, basically. So these are some studies as what I've done with the students from UTP as well. So we have this AGRU from the simulation and also from the data. So we try to converge the information all together. This is also another one. So we have two options on handling the acid gas. Is it the closed process, or is it that the wet gas sulfuric acid of Haldor Topsoe? At which capacities and then concentrations, which unit is then better than the other unit. There's also integrated refinery and biorefinery. So we make the model, and then we generate data, and then from that data we make a regressions model, and then that regression model we put it in GAMS in optimization software, so that we can then optimize it for our own purpose. And this is also like another gas dehydration unit. So this is then the target. This is then the current operation. So this current operations has the solvent, water reflux, ribose temperature, lean glycol. So they are operating it at these numbers. So in order to go down in the readability, they have to operating it using these numbers. So it's more like this Google map. So you have to turn right over here, turn left over there. So you, instead of solvent 1.6, you have to reduce the solvent to 1.38. So it gives us like a guideline or guidance on the process, so the operators know what to do. So it's more like another set of solutions. There are many solutions. Each of these dots, it represents all of these handles, the independent variables. We'll skip this, and then there are many examples there. So lastly, before I think I have 3 minutes left. So hybrid modeling in symmetry. So internally, like I said, we are using symmetry, and then this latest versions of symmetry has hybrid modeling approach, which we can use. The one that I've done personally, so we have this CFD first principle based regression. So this is the old days before the hybrid modeling of symmetry was released. Yeah, so we have the CFD modeling of wells, like oil wells, and then I make a model of the outlet temperature and then a pressure drop, and then put it into this process calculator. So it acts like like our wells, like these wells, and then it goes to it is being connected to the Rankine cycle, so that we can then have we can then do some more analytics on this. So that's an example that I've done. I think it was published this year, but I've done this work in 2019. If we use the current versions of symmetry, so my colleagues as well, they've made this CFD modeling, and then from this CFD modeling we have like 1, 2, 3, 4, 5 things that we can change. Things that we can change. For example, the velocity, the amount of sand, the velocity of liquid, the velocity of gas, and so on and so forth. Then from here we can then calculate what is then, or we can then predict what is then the erosion rate. So this erosion rate. So this middle part is then the how we then deploy this model into a web page, and then on the right side is then how we deploy that model into symmetry. So these numbers is exactly the same numbers as this one. So it's just then deploy in symmetry. The other one is then I have this gas dehydration unit. So we have a gas coming, we have glycol running throughout the system. So it is then the glycol line. So and then this regeneration column. So all of this is what we have on the field. And then I ran enough experiments. So we have also field data. So combining these two informations of field data and then this model, we can then squeeze this model into one unit operations basically. So where it then takes into account all independent variables that we are using. For example, reflux is something that we control. Reflux is something that we control. The solvent is also something that we control. Ribose temperature, the lean glycol, the glycol flow rate is also something that we control. So if we then can control this and we use them as inputs, we can then calculate or predict what would be the water dew point, what would be the reboilability, and so on and so forth. So this is then basically what's in here. So what's in here is basically in this box only. So we have input where we can then change from here. So I can then change the input. It will then be transported into here, and then from this input we have the calculated values on the reboilability, water dew point, and so on and so forth. So this can be replaced by a single unit. So it doesn't have any convergence problem. It doesn't have any recycle problems. Also, it's then solved in fractions of seconds instead of this model. It will take some time to solve, and it will also take some iterations to close all of the recycles. This is one of the latest that I've done as well. So I have this plant somewhere in the Netherlands. So I know this plant by heart. This is then the DME from methanol dehydration to make the DME. So we have a reactor with the kinetics. We have two distillation columns in series and then a recycle. This process, even though it's simple, but it is not that easy numerically because of these kinetics. distillation columns and then the recycle. So sometimes we get the solutions, sometimes we don't get the solutions, and then we have to tweak the distillation columns and then the splitter and so on and so forth. But then if I replace this distillation column with this neural network model, and then replace this as well with that neural network model, these simulations, so I just copy paste the above to the bottom, and this simulation solves much faster than this one. Yeah, so this will take some seconds or minutes depending on the variations that we apply. This will then solve in less than a second compared to this guy. So it's also another example on the hybrid. So we know that this is a hybrid. Yeah, so we have the machine learning model combined with the first principle model. I think I've shared what I think I can share in this 40 minutes roughly. So if there is any questions, please let me know. Yeah. Now I'm opening the chat.
So far, no question.
Okay.
Students, if you have any questions, please leave it in the chat box. You can also raise your hand and turn on the mic and ask if you want.
I know what I've been presenting is more like I don't know. It's something more. You need more time to study and digest, and then nonetheless it is there, and then you can revisit my my recording later on if you want to know more. Just now, please ask me questions. Yeah.
True. Perhaps you can tell a bit more what is the advantage of using machine learning compared to the simulation in the hybrid model just now. If you don't do machine learning, you can still run the scenario using Icon or your simulation model. But what is the advantage of really when you have what do you call it, the machine learning tool? Would you get faster, or is that more accurate, or what?
You can see my screen. Yeah. Here I have no, I need to how to make it smaller. So it's basically the same as the one that I showed earlier. Gas dehydration unit. Bear with me. So it's it feels a bit slow now. I don't know why. We have this. Come on. So we have this gas dehydration unit plant. So this is then the plant. So we have the feed gas coming in. We have the glycols running through the system, and we have like 1, 2, 3, 4 recycle streams. Yeah, 4 recycle streams where we have to converge. If we say, for example, yeah, if we change this, let me model comparison. So all of this are in here. So this is then the machine learning model is over here, mimicking the whole flow sheet. Yeah, mimicking the whole flow sheet. So I have this. No, it takes some time. Bear with me. It's not supposed to be behaving this way, but somehow I'm going to show you. So in symmetry here. It works like a VCO. Yeah. So if we enable enable hybrid modeling, it means we are opening this hybrid model tab, and then when we go to this tab, we can then load a machine learning model, the ML model, and then we can then tick activate, and then this input to the models are available, which we can then key in, and then once we key in all of the input variables, and then we'll then get the output variables calculated. What I have over here is I've compared the first principle model with the machine learning model. See, for example, I have this input, and this input goes to the first principle model, and then I have another input that goes to the machine learning model. So you can see that 355 is then the flow rate to the feed gas flow rate. So 355 is then the feed gas flow rate over here. And then from here, yeah, we'll then this is then our feed gas. So I'm hoping that this is also like 355. It's very slow. I don't know why. So this 355, we know that this number, yeah, 355 million scuffs. So if I change this to 355 to something, for example, 360. So I'm now changing input to the first principle and see what happens. So if I change this, this will change, and then that will change as well. So it's now updating display, and I will then try to calculate the new input. See, you can see how the calculations are run. So we can see in symmetry, we can see which unit is now doing the calculations. It will then take some time. See, it will do this iteration and stuff. So until then, we don't have any results in the first principle model, basically. So you can imagine now, if we have this model into the plant deployed, so that the operators can use this model, and then if they want to do like a sensitivity analysis, like for example, we are now having gas flow rate 360 instead of 355. What happens to the water dew point, for example, if they want to do that? That means they have to go to this model and then change this, and then they will have to wait for some minutes, so they can go get some teh tarik or kopi tarik or whatnot, or maybe roti canai, and then they come back, and then hopefully the simulation will converge. So it takes some time. Maybe also adding to this that my computer is now very slow for today, which I don't know why. So it takes more time, not even some time.
Maybe because you have Teams running.
Could be.
Meaning that if I have a machine learning model, the time that I need to run the simulation is faster than running simulation.
That is then the expected one. So I will then because I need this to finish, and then I will then show you the input to the machine learning, and then we can then compare the time taken to solve the same problem. Can I do so? I normally cannot do so, because it's now doing some calculations, so I cannot do another calculations within the same file.
How much time you need to build this model,
depending on this, because it's also very much depending on the complexity of the model that we have in this model. Somehow, even though it's simple, it's simple, only like 3 distillation columns, basically 3 distillation columns, the absorber, the regenerator column, and then the stripper. So 3 columns with these 4 recycles, and also depending on the bounds, the variables. So because we cannot like having a very low reflux or very high reflux, otherwise the column will then flood and it doesn't converge. So in this particular case, if I'm being very careful on the inputs to run the experiments, it took me, in this particular case, it took me like 6 days, day and night. 6 days, day and night. So I let the simulation run as well during the night. To create for me, I supposed to have like more than 20,000 data points, but this particular model, it doesn't converge that easily. So I got only like about 5,000 to 6,000 converged simulations from that 6 days and night. And then these 5,000 simulations, I developed the machine learning model and then make the codes on the symmetry. So this developing the machine learning model is very easy because that is not the biggest that is not the most difficult part. So it took me like another 2 days to develop the acceptable, accurate machine learning models. Another 1 day to deploy this. So all in all, it's about 9 to 10 days to make this unit, Dominic. So now I'm getting impatient. I'll close the solver. I'll stop this. Stop. Yes. So I don't want to.
So I guess you need to talk to the engineers in the plant to get some data for verification as well, right?
Yeah. This is basically the verified data, Dominic. already a verified data. We can discuss this in detail in another session, yeah, but this is already a verified data. Means the run, yes, I'm saying yes. So the run is this oh, it doesn't want to stop, yeah. So yum. Okay, I'll close this and then I'll change this to 360. 360. Okay. 360. Yeah, and activate this. Now I see everything's mixing up. It's supposed to be very quick. It's very slow. I cannot move. I couldn't even move this. I'll have to open the other guy. It's very slow. So basically, this one is done. So, need to put this up, close this. See, as soon as I change this to 360, everything here is calculated already. So I get the results. It's just that result is not being imported here because this guy is still busy calculating the first principle one. So it's not imported in this page in this column, but we have the results over here already. Quick. So when we deploy this model on the field, the engines can then easily change the inputs and then see what happens in a very quick way compared to this first principle calculations, which already take like some minutes to converge. I hope that that shed some light, some a little bit there. While waiting for this to converge, is there any other questions? Why is this so slow?
No, I don't see any questions.
Come on, students, please ask me questions. So how's simulating life, yeah? So is that an interesting course or whatnot? Because I keep telling them students as well, this simulation is just like a calculator with some thermodynamic models behind it, yeah. So in making this hybrid model as well, we need to know, or we need to understand fully what are the independent variables and what are the dependent variables, and then what sort of data that we need. So answering these 3 questions will take much more time than generating data and then getting the machine learning model. Because it takes a deep understanding on how the process behaves, and then a deep understanding as well on knowing the limit of the process equipment, because we cannot just run from 0 until infinity. We need to know the limit.
I think they are fine. Right, thanks. This, well, in your subsidiary, because you get to use Icon, I don't think the other parts of Petronas have this simulation software, isn't it? So what these people use in the plant if there's no simulation software?
We have in some of the plants we have a server, and then and then we install this Icon in that server, and then they can then have access to that server. So that's the workaround that we do basically now.
So they can still run it if they want to.
If they want to, they can have access and then run it. We are thinking to have our own server, and GTS runs the server, because now the server is on the site. Yeah, server is on the site. But now we are thinking to have the server on our site, so that we can then deploy all the models here, and then they can then have access to our server. So that's what we are thinking in the future.
That's good. But how many of them will like to do it, or they will call you to do it for them?
Developing this, obviously, they will then call us. But running this, because we let this run 24/7. Basically, all of these models we let this run 24/7, and then obviously sometimes there are hiccups and here and there, and then they will then call us. Okay, so what is then the problem now? I see that the model should run, but it gives some this problem, and then we look into the model. Sometimes maybe because of I don't know, maybe the electricity went out, and then any IT stuff that we also don't know. In the end, we have to go and then solve it.
True. That's sometimes it takes time. Good. Any questions from students? No. Oh, Dr. Chan is also here. Our another colleague.
Okay.
Is also co-teaching. We teach half each of us.
Okay.
I don't know if you have met her, Dr. Chan Yijing.
No.
She also teaches the dynamic simulation.
Okay. Very good.
Do you do any work on dynamic simulation?
Yeah, we do dynamic simulations for mostly in process control and process safety. So one of the last projects that I've done is we had these columns, and then these columns, it has several process safety valves, and then during the HAZOP there was a concern on whether these safety valves were not adequately sized. So we take the data sheets of the safety valves, the data sheet of the distillation columns, and then the arrangements of the pipings and hydraulics around the system, and then we model that in this icon, and then we introduce some deviations, for example, the cooling water failure or reflux failure, and then see how the pressure build up in the column. So that's one of the dynamic study that we have done. Another one is then the gas system. We have offshore platform where we then model the new control setup in the gas system. These two are basically if we were to know how safe or how much time we do the dynamic simulation.
Oh, that's good. Probably Dr. Chan can invite you for her lecture next time.
Okay, no worry, no problem.
Okay, I think let's call it a day. They are going for next class probably.
Okay.
Hey, thanks for your time.
Thank you.
Actually, on the screen now, this is the model comparison.
No, it's not there. So I stopped this. So we have this ML model already transported, but then the first principle model is not solved yet.
Oh, okay.
Will take some time.
How do you differentiate between first principle and second principle again? First principle is base mass balance.
Yeah, so first principle is what we know. So it's this mechanistic detail that we know, the mass energy balance, the thermodynamic models. This thermodynamic model is basically also a part of because we know the thermodynamic model is this PV NRT, and we have R there as the unknowns, and then all of this is basically a regression, so to say. Nonetheless, if we have like a black box like this, we can call this like data analytics model, and then the conventional simulation, conventional unit operations like this, we call it first principle model.
What about the machine learning model? Is that first principle or second principle?
There is no second principle. I don't see any second principle. But the machine learning model is basically this machine learning model, the regression model, so to say.
Okay. So there's only first principle model, no second principle.
No second principle. Otherwise, other people would then ask, what is then the third principle? No. So first principle is basically the physics-based model that we know, the mechanistic model that we know.
Okay, good. Hey, thanks for your time.
Thank you, Dominic. I'm running out of my battery as well.
Right. Catch up again when we go to KLCC.
Yeah. Thank you. Let me know, yeah?
Hey, thanks very much. Students, please make sure you sign attendance. All right.
Thank you.
Thanks, Dufan. Thanks for your time. Thanks for sharing with us.
Yeah,
I appreciate
no problem.
your knowledge and time. Catch you then.